We'll get some extension cords in the break. So you've got power. They've stolen one. We'll get one in the break.
Okay.
Yeah.
We'll manage until?
I think 45 minutes. Okay, so welcome back. This is the second lecture, so today is where we start to get into statistical concepts. Yesterday we tried to restrict ourselves to data and programming concepts in the afternoon and some more general perspective at the beginning of the day. And in terms of what we got done in the practical session yesterday, we actually got fairly far. We simulated our own data set, we visualized it, we made some summary statistics, and we did a very simple analysis, even though you couldn't really understand that analysis without the material that you're going to get today. So all of these data and programming concepts are what we're going to build on in the afternoon. And the hope is that I won't introduce too many new programming concepts, maybe a couple more for plotting. But that plotting stuff will be different ways of looking at the sort of theoretical conceptual material that I'll go through today. So it's a slowly building on what you learned yesterday process, hopefully. And I'll try to keep to lunch, so hopefully I'll finish this theory part by 11:30 with breaks in between, and I'll just take breaks when people start to look like they're desperate for whatever reason. You have coffee, so that means we can make it longer. So in the interest of sort of building on what we did yesterday, we'll start today from some statistical concepts that you've already encountered without necessarily seeing that they're statistical. And so they are population. We talked about a population and how you want to get information about a population. That's what you want to know about. We talked about a sample. That's where you get the information from in order to make the inference to the population. We talked about explanation, and that's the process whereby you construct some account that can account for existing phenomena and predict new phenomena. And we didn't talk about within and between subjects experiments because we're in such a humanistic context that nobody here works with experimentation anyway. But we will cover this topic when we do the statistics part, and we will cover it in the exercises as well. And the idea here is that sometimes you've got relationships in your data that you need to capture. So if you're measuring the same person twice, so if you're doing a drug trial, which would be experimental, and you're giving a placebo to one group and a drug to another group, but you're measuring before and after you take the drug, there's a dependency in the before and after. It's the same person that takes the drug. So there's a lot of stuff that stays constant, and sometimes we want to keep track of that. And it doesn't have to be the same person. As you'll see in some of the examples today, it could be the same country, it could be the same model of car, it could be something about the entity that you're measuring that stays stable, that you want to keep track of. We won't be getting into too much detail on how to do that in the linear modelling framework that I'll be talking about, but I want to raise the issue of this dependence on individuals and entities. And so we'll talk about that today in the context of t-tests. So these are all concepts that are familiar to you, that you've heard of before. And in this lecture I'm going to basically, what we're going to do is we're going to cash out these concepts in this statistical terminology. In a terminology that can be quantified and turned into numbers and turned into statistical distributions. So we're going to represent these concepts as frequency distributions and statistical parameters. So we're going to take this concept of population and express that in terms of frequency distributions and statistical parameters. We're going to take this concept of a sample and express this in terms of sampling distributions and sample statistics. We're going to talk about explanation in the context of one particular way of modelling data, and that's the normal distribution. And I'll explain the normal distribution, which I introduced to you yesterday. I'll explain this as one very simple explanatory statistical model. And remember what an explanation is. An explanation is something where you're making a bunch of assumptions in order to capture known phenomena in order to make predictions about unknown phenomena. And that's what the distributions do for us in statistics generally. And the one that we'll use is the normal distribution. In terms of prediction, we'll cash this out in terms of hypothesis testing, and here I'll explain z-scores, p-values of test statistics. And This is very much within that hypothesis testing framework that I introduced yesterday. That framework of we generate a hypothesis within sort of logical empiricism, we derive a hypothesis from our theoretical explanation, and then we test it in the world. With all of the caveats against that kind of statistics that I gave you yesterday. And for this last part, we'll talk about the t-test specifically, and talk about paired and independent samples t-tests as two different kinds of t-tests. One that respects this sort of stability and structure between entities across time periods and across different contexts, and one that doesn't. So really we're still building from lecture 1. So even though lecture 1 felt more like a philosophy lecture and didn't really have any statistics in it, it actually had all the statistical conceptual framework that you need. It just didn't have the numbers and the figures. So what we're going to do today is go through those numbers and figures and re-express everything we did yesterday in statistical terms. So you remember that yesterday I gave you this schematic where what you do when you're doing quantitative research is you're starting with your concept, your conceptual theory, that you then need to operationally define because the concepts we work with aren't directly measurable, so you need to define them in terms of something that is. Gender equality in terms of pay gap. Then you need to go out and find a dependent variable in a sample, and then you need to make an inference from what you measure in that dependent variable in that sample, that group of people that you measure, or that group of entities that you measure. You need to make an inference to the population in the real world, and then make an inference to population at relevant times. And that will tell you something about reality that you don't have access to. You don't have access to the real world. Remember, we're working within the framework of logical empiricism here. We don't know the real world, we only know phenomena. We use our imagination to connect phenomena, and that imagination is theory. So this is all very humanistically friendly. So we never get access to reality, we make inference to reality through our sample data. And so the way that we do that, in terms of today's terminology, is we express our theory in terms of a statistical model. And you can do this really, really sophisticated. So you can have a Bayesian statistical model, which has all the distributions you need to express your theory in elegant detail so that you've got a very explicit, well worked out theory of the data generating processes. And you can take very, very high level conceptual stuff and re-express it very, very mathematically. We're not going to do that. We're going to start to do that. And this is essentially what you're doing when you're saying something is normally distributed, really. You have a statistical model of the world that's on the basis of your theory. Even if you're saying something as straightforward as there's a difference between two populations, you're still applying a statistical model. And so that's what you're going to do today. And reality for us is going to be our population statistic, and that's the thing that we don't have access to. And remember I said that even in epidemiology, in Denmark, where you have the registries, where you have the entire population, you still don't have the population statistic. Because if one child is born, that's an incomplete data set. And the way that we do that is through our sample statistic, which we do have access to. And we need to relate our sample statistic to our population statistic. And we do that using our statistical model via this process of hypothesis testing that I'm going to explain today. So that's the schematic for today, relating to the schematic for yesterday. Any questions about that so far? Yes?
Will there be, at any point, be discussions of non-parametric methods?
Not in this context. No. We've only got 3 days.
Okay, fine, okay.
We can talk about it another time.
Okay.
But no. Okay, so let's get started on frequency distributions and statistical parameters, which is sort of our first step. And the way I'm going to do this is in the context of a coherent example. I come from a mining town. I come from a psychology department where we had a very powerful industrial organisational wing and a very powerful stress research wing. So my example comes from this context. This is the sort of consulting work that I might have ended up doing as a psychologist in Australia. So here's my example. And this is, we have to imagine ourselves, we're a consulting firm and we're in this scenario. And this is the example that's going to run through the whole lecture. So we're psychologists, we're a team of psychologists, we're employed by a mining company and they want us to measure chronic stress among their employees. So that's our brief. And so we translate their question into a research question. It's got all of the concepts and everything in it that we're familiar with when we sort of start conceptually framing a research question. So we frame that in terms of a research question that this is what we're used to doing when we're starting our own research projects. Are workers at this particular mine suffering from chronic stress? So the next thing we need to do then is to find an operational definition. So you can't measure stress directly. Stress exists as a psychological social construct with all that entails. We need to define it in terms of something that's measurable. And let's say we do that in terms of elevated levels of blood cortisol. So we've got a very biological definition of stress. And already you can see we've made a choice, right? We talked about this yesterday. There's other ways that we could define stress. We could define stress more psychologically, we could define stress more socially, we could define stress in terms of other parameters. But now we're making a reductive biological choice to define it in terms of blood cortisol. So that gives us our dependent variable, which is blood cortisol in micrograms per deciliter. That's normally how you measure blood cortisol. So the first thing we do now that we've got our operational definition all set up, we've done sort of the left side of that schematic, is that we need to start thinking about this in terms of hypothesis testing. And so the first thing you do in this statistical null hypothesis testing framework is you come up with a null hypothesis. You say, what would happen if there was no stress? That's always the first step you do. So our null hypothesis is that the miner's blood cortisol at this mine is within the normal range. And the normal range is 6 to 23 micrograms of blood cortisol per deciliter. So that's normal. So our null hypothesis is that the mine workers don't have a higher blood cortisol than 23 micrograms per deciliter. Again, there's another choice here, right? So we've said that we're going to go for the upper boundary. And that's what we're going to define as chronic stress. So from here we have an alternative hypothesis. The next step we take here in this hypothesis testing framework. Yeah.
Going one sentence back,
yeah.
We are defining. You said we are going for the upper boundary. What do you mean?
We're saying that we're defining stress as anything higher than 23 micrograms per deciliter.
Okay.
Because that's the normal range.
Okay.
And that's a choice. You don't have to do it that way. You could say that this mine's more stressed than the average mine. Or this mine is more stressed than the average burner hill.
Okay.
Or this mine is more stressed than the average player. So we're choosing as our reference this already predefined thing that's not objectively meaningful outside of our social construction of what's normal stress. So and I just want to do this to highlight that you're always, so this is super biologically reductive, right? We're something where we should have objective truth, but we still don't. And so from our null hypothesis, we know what things would look like if the mine was fine. What would the mine look like if there was a problem? What would the mine look like if the miners were stressed? So our alternative hypothesis then is that the mine's workers do have a higher blood cortisol level than 23 micrograms per deciliter. So any number higher than that is chronic stress. And we want to know on average. We don't want to know if there's just one miner who's chronically stressed, because that doesn't say anything about the organisational context. Or it might not. We don't know if it's 10. We want to know if it's the mine generally. So we want to know if, on average, the mine's workers are stressed. There's two ways to do this research. One way is to collect data from all of the miners and just see what the average is. And then you don't need statistics. Well, you do need statistics, you need the average. The other way is to collect data from a sample. So let's go through this sort of strategy one. And why wouldn't you do this in all cases? Because it's going to cost more money to collect stress results and run it through a lab for an entire organisation. So you might be outcompeted by another firm who can only do it with a smaller sample. So even when the whole population's accessible, you've still got social constraints on the way you design your research. So let's start with this strategy and collect data from all miners and just see what that looks like. Okay, so here's our mine, and here are our miners. And this is our population, basically. So we've got the population now. So this is the equivalent of what they've got over at epidemiology in their registries. Only the population has all Danes in it. So this is everybody combined. They don't look particularly stressed. And we have this person, and we denote this person with x1, little x1. That's this person's score, their cortisol score. This is x3, that's his cortisol score. It's x2, that's her cortisol score. And we can look at the population cortisol by just taking all of the x's. So x1 has a cortisol score of 14. x2, this one down here, has a cortisol score of 24. x3 has a cortisol score of 17. x4, x5, and so on until we get to x48, because we've got 48 minors. It's a little operation. So how can we represent this data? So we can't go back to the mining company, to the HR at the mining company, with just a sheet of paper that's got a list of 48 scores on it. It's not really as informative. It's not optimal in any case. So we need to process this data for them somehow. So how do we do that? Well, one way to do that is to look at the frequency of each score. The distribution of the different scores in terms of their frequency. And we can do that because we've got all of the scores. So what does frequency mean? Frequency, just sort of literal translation. This is one of the nice things about statistics, is a lot of the work was done in the 20s, so they use a lot of normal words. It wasn't done back in the old days when they were using Latin. So frequency just means frequency, often-ness. So how often does a type of score occur? How frequent is a type of score? So if we take our mining data and do this exercise, we can divide the scores up into bins. And again, this is a choice. This is a research choice for representing this data. So let's look at all of the miners, say, with all of the scores. How many scores are there between 0 and 5? How many scores are there between 6 and 10? So basically intervals of 5. And here there's none. Nobody's got that low levels of cortisol. There's one relatively chilled out miner who's got a score between 11 and 15. This is a more sort of common score, 16 and 20. This is a very common score, 21 to 25. It becomes less common, 26 to 30. So there's sort of a, sorry?
Is that a stupid choice? If 23 is the cutoff point?
Why is that?
I was just thinking, if 23 is the point where you're stressed,
Yes.
why have a level called 21 to 25?
That would be a stupid decision. Well, actually, not necessarily, because we want to see what the mean of the population is. So it doesn't really matter for this one, actually.
Okay.
Because you're not trying to cut out people that are too stressed and single them out. You're trying to look at what the average of the population is and relate it to this cutoff point. So actually, it doesn't really matter in this case.
But wouldn't it be nice to have a cutoff point saying this many of your minors are actually over the limit?
That would be a different sort of question, yeah. You're the first person to raise that in many lectures.
Okay.
But thank you. But you get the idea, right?
Mm.
And this looks like, you can see that this looks roughly like what real data would look like. I don't know if it relates. This is a fictional example. I've simulated all of this data. I don't know if this is real numbers. I don't know if this is what any given organisation would look like. But generally, like we saw with the heights data yesterday, there's a value that's most frequent, and that value seems to be in the sort of the middle of the kinds of values that you can get, and then it tapers off on either side. Yeah?
But thinking as a consultant, it's also interesting that when you add categories that actually don't have any people in it, you're sort of opening up a latitude space for people, like, because if you're adding the last one going, where there's nobody, you're sort of marking, well, at least nobody's there.
Yeah,
you're sort of indirectly patting them on the back.
Yeah.
But it going in the other way, you're sort of...
Yeah, so what you don't include...
Yeah, and so you're signaling quite a lot. Whereas if you want them to look bad, you definitely shouldn't, like you want to alert to stress problems, you wouldn't include the last one that's blank.
Nope, and that's all choices in your visualization. So even here is a very simple visualization. This is just where I had no intention whatsoever. I just wanted to make some crosses that sort of looks like a graph. And even here, there's normative information that gets communicated. So be aware of that. But this then, that's frequencies, and those frequencies are distributed. And that gives us something that we call a frequency distribution. So that's what we mean when we say distribution. How are the scores distributed, verdeelt, in terms of their frequency? So that when someone says a frequency distribution, that's what they mean. It's also called a histogram. So this is a plot representing how often each type of score occurs. And normally they don't look like this, normally they look like this. Yeah?
What would happen if we made a scatter plot instead? I mean,
Here we only have one variable.
sorry?
Here we only have one variable though.
Okay.
So a scatter plot relates two variables,
Yeah, all right. Yeah.
and here we only have the one variable, so we'd have a scatter plot, but we just have basically a line. Yeah. And the line would kind of look like a frequency, a normal distribution if you looked at it. Yeah.
Okay. Yes.
Yeah. So here we only have the one variable. So this is just tells us the frequencies, and this is what a frequency distribution looks like. So when you hear the word frequency distribution or histogram, picture this in your mind. Yeah.
So how would it be smart to visualize it? Because assuming these miners all work in different subsections of the mine.
Yes.
So some are mechanics and some are actually physically hammering away at the mine or whatever they do. I guess.
Can tell you're married to someone from a mining community.
So couldn't you make I don't know how, but couldn't you make a graph that would illustrate like
Subgroups?
where the stress levels, like which subgroup is freaking
That's
out?
what we get to when we start talking about paired and independent sample t-tests.
Okay.
Yeah. But so yes, very good. And you might be interested in subgroups, and that's what your consulting job could be. So that's all we mean when we say histogram. So if we've got our population, which is the mine, we can go and give a list of data, or we can process that data a little bit and give this graph. And if you gave this graph to the company, they might start to worry and say, oh, okay, I can see we might have a problem with chronic stress. Yeah.
If you wanted to do like Kirsten talked about, like putting the line where you consider it stress,
Yeah.
would it then be like a false representation if you did like a histogram that had one column that said not stress and one that said stress, because you're supposed to have bins of the same size? Or could you do that, or would it be called something else? Or maybe it's not called bins, but the
Yeah, they are called bins, yeah.
But
So you could arrange your bins so that it fell out the right way. Actually, but you'd be better off doing it as a probability distribution, which we'll get to later,
okay.
and then putting the line, which would be a cutoff.
Yeah.
So I'll talk about that when we get to probability distributions, because probability distributions smooth over all of these bins. But yeah, it wouldn't. There's no such thing as a false representation.
Really?
There's more or less transparent. Or better said, everything's a false representation.
Yeah.
Everything involves choice, right?
Yeah.
So the only true representation of stress in the mine is this one. There's a list of numbers. Wait. Yeah. Yeah.
Yeah, I know, I look very skeptical.
Yeah.
Sorry. But it's just, yeah, that's already a sample, right?
That's
That's
well.
already a sample, and that's already making things into numbers.
So there's
So-
exactly. So it's not really true either, because it's
I much more like you. There's no true representation because that would be
100%.
reality,
Yeah.
right? It's,
So even though we've got the
that would
population,
that what you it would be what's happening, and that's
Yeah.
not possible to represent.
so this is a true representation of the population at that time of the blood levels of cortisol, not of stress. so this is an important thing to consider. So there is a lot of philosophy going on, even when you're not doing philosophy. But essentially what we're trying to do is to be informative and transparent. And so what you want to do when you're doing science is create visualizations that are informative relative to your research question and where your choices are transparent. And then make all of your materials, all of your data and all of your code available so that people can try to reproduce the same thing. And they can say, well, what if I bin this differently to the way they did? How does it look? And that's the aim, because science then becomes something that's intersubjective, not subjective or objective. And that's all you can do is intersubjectivity, and even though this is not what the open science movement talks about, people who talk about open science are really talking about sort of biting the bullet on saying science is an intersubjective thing. Even though they're very objectivist and logical positivist. So philosophy aside, is there a more concise way to represent this data than this graph? can we give the same information in a more condensed form? So essentially what we're trying to do is boil things down, boil things down, boil things down, and then make very simple inferences, which can be dangerous, but that's the process that we go through when we use this method. So we can, and we can do that in terms of the mean. We can do that in terms of the average. We can do that in terms of the population average. So what's the population average? What's the population mean? We talked about averages yesterday. All an average is something that you get when you add up all of the numbers that you've measured and then divide it by the number of numbers that you've got. And we were comfortable with that yesterday. So for example, we take all of these x's, x1, x2, x3, x4, x5, x6, and so on up to x48, and then divide it by 48. That's how you calculate the average. And there's an equation to calculate the population mean, and that looks like this. So I present this in this format to demystify some of the notation here. And what I want to demystify for you is this capital sigma here. And normally sort of when you put this up, if you sort of just start with this, you can lose a lot of people. But there's really nothing to be afraid of when you see a Greek letter, because a Greek letter just means something. It's just a way of condensing and simplifying things. It's just a way of, it's a shorthand. It's a shorthand for the logic of what you're doing. All the sigma means is add everything together that comes after the sigma. So it's a sum. So it says for all x of I, where I just means a variable of one of these numbers, from 1 to however many things you've got, add. And then divide by the number of things you've got. Is everybody comfortable with that notation? We'll come back to it. Yeah?
So is it relevant? I just don't get why they're all called x2. Why isn't it x1, x2, x3? For different people.
x1, x2, x3,
Oh, they are.
x4.
Okay,
You're just sitting too far away. Yeah. And we're just using x as a shorthand for keeping track of people, and the subscript is just which person it is. So x is their cortisol score. If we went out and measured their height, that would be another letter, and then the 1 would be the person.
Is it a 1 or an L?
Which one? Up the top?
1 just after the equal sign on top. It's 1. Okay.
That's a 1.
So, and the one below is index 1.
x1, x2.
No, not there in the equation.
Down here.
Down here?
Yeah.
That's an I.
Yeah, I know.
That's a 1.
That's a 1, and the other one is the one in the upper left.
And that's a 1, yeah.
Thanks.
They're 1s.
And the I is the index.
The I is the index.
Yeah.
And we did indexing yesterday.
Yeah.
So you can imagine how you could program this actually. You would have the hard brackets. So all these subscripts do for you is they're a hard bracket. Yeah?
What I think many find confusing because we don't remember is that there's a what call it star. Actually, if you wrote a star between 1 divided by 8.
Ah,
You know,
yes.
it's basic stuff.
Thank
that
you.
when
Yeah,
I look
yeah.
at it, it's sort of hard to remember that.
Thank you.
It's actually like a, what do you call it?
At times. So yeah, so that's very, you're very helpful with this beginner empathy stuff.
Yeah.
There's should be a times.
Yeah.
So this is 1 divided by n times the sum of everything.
Exactly.
Yeah.
So the sum goes to the top.
Yeah.
And
Exactly. Which would be the equivalent of just putting a line here and putting an n underneath it, but that wouldn't look pretty.
yeah, exactly.
Yeah.
You said the right part meant from 1 to the last one, then add them all together.
Yeah.
Which one is adding?
This is the adding.
Okay.
So that sigma means add. And you can just think of it as an S for sum. So sum everything after this. Yeah? Yeah?
Would it be possible to just calculate 1?
Sorry?
To just calculate something on the board?
I can sort of draw it out to give you an
Yeah.
example. Yeah. So I'll just do a simple one. So x1 is equal to say 5. I'm bad at mental calculation, so I'm going to need help. x2 is equal to 7. x3 is equal to 3. try to be merciful on myself, x4 is equal to 5. And then what we want to say is we want the mean. Mean is Greek letter mu. This is the
thingamajig.
Yeah. That's the thingamajig, that's the Greek letter mu. And the Greek letter mu is just the Greek m for mean. And that is equal to 1 divided by n. 1 divided by n. So here, what's n? 4. Times, and this is a separate thing, so you can put that in brackets, times sigma of xi. So add all of the xi's from I is equal to 1 to I is equal to n. Have I made any mistakes?
There's no I equal to n, but maybe that's just what it is.
In the top
Yeah,
it's just
that's right. You can do it both ways. I is equal to, actually I think that's not the conventional way.
So the n on top would be 4 here.
The n on top would be 4.
Yeah.
So that means that we go through this process of saying what's x1? So we go over here, we go to 5. So 5. Well, first let's do it in the right order, right? So this is 1 divided by n. So now we're going to write this out in full form. 1 divided by 4 times. And then we want to put a bracket here. So x1 is 5. And then the sigma tells us to plus 7. And the sigma tells us to plus 3. So this is sort of a recipe. It's kind of like the code that you write. So now we have to add all of those together and times it by 1 divided by 4. That's 5 plus 7 plus 3 plus, so that's 20. 1 divided by 4 times 20 equals 5. So the average of that is 5. And the notation for doing that is just, when all the sigma does is it shortens this stuff down so that you can write it in a very short format without having to write everything out explicitly in your math paper. Yeah?
So normally do mathematicians call it the sum function?
Sum function.
Sum function, okay. Yeah, and just a tip in spreadsheets, normally the sum is also shown as this icon, as an icon representing sigma.
Yeah.
So
okay.
People use it daily, I think.
So there you go, it's in Excel. Cool. But this is all good that you're sort of adding these different labels to put on this thing, because the more labels we have, the more hooks that we can hang on it, the more comfortable we get with it. And this is sort of a simple context, but this notation will come back again. Okay, so basically that one there means the ith score, that one there means add everything, that one's the number of subjects, and that's the statistical parameter that we're interested in, and that's our population mean. And our population mean in this case is 24.48.
Not good.
Micrograms of cortisol per deciliter of blood. So
The mining company has a problem.
the mining company has a problem. So what is a parameter? I've used this word statistical parameter. And this parameter is a very specific word in statistics. Yeah? Question? Anya? No? It's a very specific word in statistics. It means something very particular. A parameter is a number that represents something about a population. And what it represents about the population is something about its distribution. So a parameter refers to something about a distribution. So whenever you say the word parameter in statistics, that's what you're saying. Something about a distribution. And in this case, what does the population mean relative to the frequency distribution, or the distribution that I showed you before? So what does a mean mean relative to the distribution of minors? What the mean tells us is roughly the centre of the distribution that we'll be talking, at least for this sort of distribution. So it's a statistical parameter that tells us something about a population. Statistical parameter means something about a population, and what it means is something about the distribution of that population. And in this case, the mean tells us the centre. The particular parameter that we're talking about tells us about the centre of that distribution.
What could another parameter be?
This one. So another parameter could be, well, there's more information here, right? So any insights into what another parameter might be? If we wanted to describe this distribution to somebody, what information are we missing? Yeah?
How about the minimum and maximum distribution?
Minimum and maximum is not for this sort of distribution.
Okay.
Anya?
Median, standard deviation.
Standard deviation. Yeah. So standard deviation. Remember what we talked about yesterday? Do you remember when I mentioned the standard deviation? Can you remember what that was?
Yes.
The fatness of it. Yeah. And so that's the other thing about this distribution that will be informative to know. So let's do that. So the mean doesn't represent everything. There's more that we need to know. And so let's talk about the standard deviation a bit and talk about what that represents and how it represents it and how we calculate it. So let's do that by looking at smaller populations, because our population's a bit too big to sort of work with specific numbers. So let's say that we've got a little population now. We sort of step out of the mining example, specific mining example, and imagine that we're working with lots of mines of different smaller populations. So here's one population of miners where x1, measurement 1 is 23, measurement 2 is 35, measurement 3 is 26, so on. And let's plot that and see how it looks. So we're plotting it, and here on the x-axis is each subject. So this is not a visualization that you necessarily show people, but this is to give you the insight of what standard deviation is doing for you. So here's subject 1, subject 2, subject 3, subject 4, subject 5. And we're interested in their scores and how their scores relate to one another, and what statistical parameters we can use to describe those relationships. And we can see here that there's an average score that we've used calculating all of this. And that's 27. And so we've represented that with this strong blue line. So the average of this group is 27. So let's imagine population 2 now, which has a different range, different number of scores, different values for their 5 scores that they've got. 11, 44, 25, 17, and 38. That's the scores that we've got here. Okay, so let's plot that now. It looks very different, doesn't it? So subject 1's quite low, subject 2's quite high, subject 3's sort of in the middle, but the mean's the same. So these two populations are different in a very important way, even though their mean's the same. So we need to convey more information when we're telling the company whether or not they've got a problem. And what that difference is that it's the same mean, but it's still a different distribution, and that difference is in how much variability there is between the scores. So the mean tells us then, the centre, we need some sort of measurement or some sort of statistic or some sort of number, some sort of parameter to tell us about the fatness of the distribution as well, because that's the other piece of information that we need to convey if we want to summarise this table into a concise form. And so we need to know about the shape of the distribution. So these are the two parameters that this sort of distribution has, and the only two that it has. The centre of it, or the peak of it, and the shape. That's all you need to know everything about this distribution. You can regenerate it again. Actually, that's what you did yesterday. So when you generated your deer study data, what you did was you gave R norm function a mean and a standard deviation, and then it generated data on the basis of knowledge of that mean and standard deviation. So what does the standard deviation tells us? Again, statistics is nice because there's not a whole bunch of Latin that gets in the way. It's actually normal everyday words. You just have to have sort of made explicit that it's normal everyday words. It tells us the shape, it tells us how spread out the scores are, it tells us the variability, it tells us the average. We can't say average though because we've already used average, so we'll say standard. Distance, i.e. the deviation, of each score from the mean. So how far each score away is on average from the mean. That's what the standard deviation tells us. So if we come back to this picture and this sample, what do we need to calculate? We need to calculate the distance of each data point to the line. And that'll be our standard deviation. Is that intuitive?
Mm-hmm.
That'll tell us the shape. So we need to know the distance from x1 to mu, which is the mean, distance from x2 to mu, distance from x3 to mu, distance from x4 to mu, distance from x5 to mu, and then divide by the number of subjects, because we're calculating an average. Or we're calculating the average distance of each data point. So we could do this by sort of always taking the biggest number. That would make sense, right? So if we always took sort of the biggest number, so 27 minus 23, 35 minus 27, 27 minus 26, 27 minus 19, and 35 minus 27, then divided by 5, that would give us the standard deviation. That's all we need to do. That would give us 6.52. What is mu in mu is Greek? Yeah, it's the population mean, Genschnitt. Yeah, so it's this blue line, the average.
And it doesn't matter whether it's above or below.
Well, it does. That's a problem. So if we were to do this manually, we'd have to sit there and look at each data point and see which one was whether it was the line that was taller or the dot that was taller.
Yeah.
And that'd be a major hassle if we had more than 5 data points.
Yeah.
So we want something that's computationally more efficient, that's going to be able to do this for us without us having to go to each individual data point. So that's the strategy that I'm going to tell you about now. That's too inefficient. Because the mu and the data point signs keep switching. We can't just take the data point all the time, because then we won't get an accurate distance. We can't just take the mean all the time, because then we won't get an accurate distance. We need to take the highest one. It's not going to work. So if the signs keep switching, they'll keep cancelling everything out and everything will be messed up. So to solve that, we just get rid of the sign. We square. So if you remember, 2 times 2 is 4. What's minus 2 times minus 2? It's also 4. So a minus times a minus gives a plus.
Yeah.
So that's it. So that cancels out our scores for us. We just take each distance, in this case the score minus the average, and square it. And that gives us the squared distance, which is always positive. And then we add all of those up and divide it by n. So what we're doing is we're squaring the difference between each score and the mean. Square cancels out the sign, but this doesn't give us what we wanted, because what we wanted is the average distance. This gives us the summed average of the summed differences. Sorry, the square of the summed differences. It doesn't give us the average of the distances, because we've squared things. We need to get rid of that square. But this is still a number in statistics. This is called the variance. So if you hear the term variance, this is what's meant. If you hear the term summed of squared errors, this is what is meant. So you can think of it as, this is an error, this is an error.
Why is it an error?
This is one of the infuriating things about statistics, is that it's not actually an error. No one's made a mistake, but statisticians sort of work in this platonic world where there's the statistics that are real and reality deviates from and this noisy, messy nonsense that exists in the illusory world deviates from that. And so it's an error relative to the pure reality and truth, which is the statistic. Okay, so the mu's reality and annoying illusory non-reality, sort of the Platonic K, gives us these things that are erroneous relative to pure truth. Think of it that way.
Okay.
That's the humanities way of thinking of it. Yeah.
So the variance is the sum of squared errors.
The variance, yeah, exactly. The variance is the sum of the squared errors. So if you hear people talk about variance, it's the last step before you get standard deviation. To get standard deviation, all you need to do is take the square root. Just unsquare everything again. Now you've got standard deviation. And that looks like this. Yeah, but it looks horrible, but it's just the same as what we were doing before, right? So remember, this is 1 divided by 5. So you can handle that. Times something that we're adding together. What are we adding together?
All the fives. Fives.
We're adding together, we have to start in the middle. Remember when we were making brackets yesterday, we started in the middle? Start in the middle. The score minus the sample mean. We're not using mu anymore. We're using something called x bar. What x bar tells us is that this is not a statistic. This is not something about the population. This is a sample statistic. This is something about a sample. So we're going our score minus the average in the sample squared for score number 1. And then adding that, our score number 2 minus the average squared. Score number 3 minus the average squared. And procedurally going over that again. So we're just following a recipe. And then timesing it by the number of measures, subjects, samples, whatever you want to call it, and then taking the square root.
And what's that thing called?
And this is called sigma.
Sigma.
That's a Greek. Sigma for standard deviation, mu for mean.
But,
Statisticians like Greek.
but it's the first one is little sigma
Yes.
for statistics, and the second one is
Yeah,
large
sorry.
sigma for
Yeah.
the sum.
Yes. That's a function. That is an object.
Yep.
In the language of yesterday.
Capital.
You could have just written SD. So all we're doing is the square of the square root of the sum of the squared errors divided by n. And the reason we're squaring is to get rid of the sign. So if you remember from high school, absolute values, same difference. Absolute values just don't look pretty on paper. So now we've got the mean, and that tells us the centre, and we've got the standard deviation, and that tells us the shape. So now we've got the population fully characterised, statistically. We've got the platonic truth of the population from a statistics from the perspective of statistics, because we've got assuming. But what are we assuming here? Yes.
Can you calculate, like, so that I can see the difference in the variance scores and the standard deviation? I mean, I have a hard time like looking at the numbers and see.
Should I go through a worked example of standard deviation?
I do.
Absolutely.
Just to make sure that
Yeah.
I get how it looks like, variance
Absolutely.
versus the standard deviation.
Well, the variance versus the standard deviation, the short answer is that the variance is the square
Yeah,
of the standard
what
deviation.
does that
But I'll go
look
through
like
it.
calculated?
But I'll go through it.
Why would you ever report just the variance and not the standard deviation?
You would use it in equations
On patients.
because you don't need to unsquare it. And if you're a Bayesian, you'll use something called the precision, and the precision is the inverse variance, just to make everybody's life horrible.
I love it.
Because Bayesians are more worried about the precision of their beliefs than they are about the standard deviation of reality. Okay, so let's say then that we've got our 4 data points again, and that these are our scores, and the average is 5. Okay, so this is our setup. And we've got our standard deviation equation. I never remember these things. What comes first? Alright. Is that copied right? Yes. Okay. So what are we doing? We're going through and we're going to now make a list, right? So we're going to make a list of stuff to sum together. So we start again by doing our 1 over n. That's 1 over 4. And then we will go through and do our sums first. And we'll leave everything under the square root for now. We'll do that last, because that's the order of operations. And then we'll time what we're going to sum together. And what we're going to sum together is a whole bunch of stuff. We're going to sum together 5 minus 5. Squared. Okay, so that's score 1 minus the average squared plus score 2 squared plus score 3 squared plus score 4 minus the mean squared. Okay? So, what's our next step? Now we need to go through and do everything inside the innermost brackets. Did I make a mistake?
No, just calculating.
Yeah. So I need to go through and do everything inside the brackets first. So we'll keep our 1 over 4 because we're not going to touch that yet. We'll keep our square root because we're not going to touch that yet. And let's sort of be a little bit more efficient and do the thing inside and then the square. Okay? So this is 0 squared, which gives 0. 7 minus 5 gives 2 squared, which is 4. 3 minus 5 gives minus 2 squared, which is also 4. Notice how everything's coming out positive. That's what we want. 5 minus 5 gives 0 squared, which is 0. So we've got 1 over 4 times 8. Take the square root. So that's 8 divided by 4. Did I make a mistake?
I think you need brackets in the second one.
Yes. Thank you. Okay, so we need to add all of these together, which gives us 8. 1 over 4 times 8 square root. That is square root of 2. That's the variance. Okay? So that's not the standard deviation yet, that's the variance.
Report it like that.
If you're reporting the variance. But if you want the standard deviation, you want to get back to sort of the distance without the square in it that you put in. That's why you're doing both of these operations. You're squaring to get rid of the minus, and then taking the square root to get back to the same scale. So take the square root of that, whatever the square root of 2 is, that's your standard deviation. And in the old days, that probably gave a nasty number to write out on paper and to work with. So the variance was probably invented as something so that you could work with just that as a unit without having to give sort of decimals. That'd be my guess.
But would you write it variance and then have the square?
It depends. It's not as informative. You'd write it as standard deviation. But now you know some people talk about variance, some people talk about standard deviation. You know the difference. Yeah?
Could you, I mean, I sort of follow how we get to the standard deviation, but could you express in human words what it is? What is it actually a measure of?
It's a measure.
I know it's.
Yeah.
I understand it's the width or the breadth or whatever it is.
It's the measure of the variance.
But if you're going back and you're talking to me at the mining company and you're trying to relay what you found out.
Yeah, that's very useful. So it's the measure of the variability.
Yes.
It's the measure of, in this mine, you've got a stress problem and everyone's roughly the same.
Yeah.
In this mine, you've got a stress problem, but you've got someone who's really relaxed, someone who's hyper, going into shock.
Yeah.
Can I try to?
Yes, that would be good.
Because if we're reading this as psychology data, you think that you need 2 radically different interventions for these groups.
Yes.
Because the
Yeah.
group, you could intervene everybody pretty much the same way because they're all sort of around the middle. So you could just target everybody with the same treatment. But in the other one, you would want to find the ones that are to the extreme, and then you want to target them. And there's actually some in the middle that you just want to leave and not do anything on.
Yeah, that's perfect.
Oh, so you probably wouldn't target the ones that were on the good side.
Well, it depends if they're...
Maybe you want to learn from them.
If they're not as good, yes.
Actually, being the head of an academic department, you might want to target the ones that
Maybe they could too.
They could do some more.
sort of look into Vipomatic and yeah.
Thank you. That
So
was
yeah,
helpful.
that's, and you might have homogeneity
Yeah.
as well. Not necessarily, but you might. So you might have all sorts of different things causing this.
Or you might look at like, okay, what is it about the people that stand out? So
Yes.
does it just happen to be, like I'm a gender researcher, so my immediate thought would be, does it just happen to be all the women that are fucking stressed? Or is it like, so that could obviously be, then you need a different kind of intervention. And
Yeah.
then it's like,
Liners.
yeah, well,
But women work in mines too.
Women work in mines too, yeah.
awesome.
Not enough according to my brother.
But you haven't told us whether they work, in offices or what.
No,
roles they
no,
occupy
exactly.
or- yeah.
Exactly. So just for the example, it's not really so important. So now we can talk about variability and the average, and that's informative. We can go back with this figure and say this is the distribution of your population, and this is the average, and this is the variability. And just like Leah says, they can make decisions on the basis of that knowledge. And we actually, if we have all of the data, we don't need to do anything else. Our consulting work is done. Yes.
In this exam, we don't have really outliers that are extreme in the sense that they are far from the mean.
No.
But what happens if we have a population where that is the case? So what will happen to the...
If you have that could potentially become interesting. So, I mean, as a diligent researcher, particularly if you're working in interventions and you see somebody who's got stress levels that are so high that there must be some sort of biological damage occurring, then you'd want to write a script that could find them, basically, because that's going to be important.
But my question was more, how will that be reflected in the standard deviation?
That could be reflected in a violation of the assumption that the data is distributed normally.
Okay.
And we'll come to that this afternoon when we get to an example about the difference between Volkswagen and Audi cars.
Okay.
So that's a really good point. My point that I was trying to allude to was that if it's only one person, you want to find them and do something about it. If it's a group, then there's something different. And if it's a group that sort of clusters out here, sort of clump here or a clump way out here, then it's a violation of a distributional assumption. Or it's worth looking at if there's two distributions. You might have a bimodal distribution.
So,
And we'll cover that when we get to the example.
but let's say I didn't have that histogram. You just present me some numbers, the standard deviation and the mean. Is there any way I can actually see our...
No, which is why you should also present the histogram.
Okay.
You should also, if it's wherever relevant, visualize things in a way that's transparent and clear, and inferences can be made from it. Yep.
I suppose it's in relation to what you're asking, because from what I've heard from some of the others, there's also the problem with the mean in that sense is that, I mean, if you had one person who's like 50, it would severely push the entire mean towards that side, even though it's only one person out of the huge sample.
And we saw our example with that yesterday, where we concluded that IKK is taller than IKS.
Because of the giant...
Because there was a 2-meter person from IKK. Actually.
You had a gender deviation.
Oh, I had a gender deviation as well.
Yeah, we were getting more women.
Oh, interesting. That's a good point.
And yeah, you would have seen that if you had taken the
Yes. But someone just got in trouble for doing that at Copenhagen. Yes. Good.
You said before that it wouldn't be interesting to look at the minimum and max and median, but wouldn't that tell us some of the same thing?
I didn't say it wouldn't be interesting.
Oh, okay.
I said that they're not statistical parameters of this kind of distribution.
Okay.
So they could potentially be interesting, but they're not statistical parameters in the sense that they don't say anything about the Platonic distribution that's generating the data.
But they would tell us something about outliers.
Yeah, and that's where you become sort of take your statistician hat off and put your researcher hat on, which are two different things. Yeah. So statisticians are Platonists. It's easier to think of it that way. Particularly frequentist statisticians, they're Platonists. Essentially what you're doing if you're a frequentist is you imagining that you could run your experiment 1,000 times in order to get to true reality. So we're living in the sort of logical positivist hack of Platonism. That is modern statistics. Or old-fashioned statistics. But that's it. That's the sort of the first step. That's frequency distributions and statistical parameters. And you've got some terms under your belt. You've got you've been introduced to the sort of sigma notation, and you've gotten the sense of the way that we can describe data sort of, and compress it down. Next we'll go on to sampling distributions. Let's have a 10-minute break.
Det er